Hello everyone. From here, in another 2-3 lectures, we are going to discuss about network reduction techniques, which is the most important part of network analysis or electric circuit analysis. These network reduction techniques includes the following topics: equivalent value of R, L, C, that is resistors, inductors and capacitive elements, in series as well as parallel connection, source transformation technique, source shifting technique, voltage divider rule, current divider rule, delta star transformation and star delta transformation. To do any analysis of electrical circuit, first we need to reduce the complexity of the network. To reduce the complexity of the network, some of the techniques that we need to apply such that we can easily get the analysis of the network. That means you can find out the required quantities, whether it is current or voltage across the branches. In this session, we are going to see the equivalent value of RLC if they are connected in series as well as the parallel combination. That means if the resistors are connected in series or parallel combination, how to find the R equivalent. Similarly, if the L and C are connected in series and the parallel combination, how to find out those equivalent values. So let us see first the resistors in series combination. Now we know by applying KVL, the sum of the voltages, that is V1 plus V2 equal to Vs. If you represent the V1 and V2 in terms of I and R, you can write this as a I into R1 plus I into R2. Similarly, Vs can be written as total current into the total resistance. So total current is I. The total resistance can also be represented as R equivalent. So if you take I common from this and cancel, you will get R equivalent as a R1 plus R2. This is the formula we need to follow if the resistors are connected in series. Now let us see in a general case if N resistors are connected in series. So the concept remains the same. You will apply the KVL to this. So algebraic sum of the voltages around the circuit equal to 0. That is, source voltage will be equal to sum of the drop across the network. If you write this expression using the Ohm's law, this becomes I into R equivalent, I into R1, I into R2 and I into Rn. So if your current gets cancelled both the sides, then we will get finally R equivalent equal to R1 plus R2 plus and so on Rn. So this N can be any number of resistors. It can be 10, it can be 100, it can be 20, anything. Now let us see if the resistors are connected in parallel combination. Now let us assume only the two resistors connected. So if you apply KCL at this point, we have sum of the entering currents, that is Is equal to sum of the leaving currents I1 plus I2. Now we know across the parallel branches the voltage remains the same. So we will apply voltage. Then if you expand this current expressions in terms of the voltage, it becomes V by R1 plus I2 becomes V by R2 and your Is becomes V by R equivalent, and the equation simplifies like this, and left hand side and right hand side we get cancelled and the rest of the equation becomes 1 by R equivalent equal to 1 by R1 plus 1 by R2. But we want the R equivalent value, not 1 by R equivalent. So therefore the R equivalent value becomes 1 whole divided by 1 by R1 plus 1 by R2. So this formula can also be simplified as R1 R2 by R1 plus R2. But I strongly recommend to use this formula instead of this. Okay. This formula can hold good for any number of resistors that you are connected. But if you use this formula for more than 2 resistors, like for 3 resistors, if you use R1, R2, R3 by R1 plus R2 plus R3, then that becomes wrong. So that is why. So try to follow the expression, this one. If it is only 2 resistors connected, then you can comfortably use this formula, R1, R2 by R1 plus R2. Now let us see for the generalized case where n resistors are connected in parallel. So this is the case. We have n resistors that are connected in parallel. That n can be 5 or 10, any number. In that case, you will write sum of the entering current, that is Is, equal to sum of the leaving currents. We assume remaining all currents are leaving. This becomes In. Then if you represent in terms of the voltages and resistors form, and by simplifying it, you will get R equivalent equal to 1 by R1 plus 1 by R2 plus and so on plus 1 by Rn. Now we will see series combination of inductors. Now let us apply KVL to this circuit. V1 plus V2 minus Vs equal to 0 and Vs equal to V1 plus V2. Now we need to write the voltage equation for inductance. In the first video itself, I have given you what are the equations for voltage and current for RLC elements. So we know that the voltage equation for the inductor is L into di by dt. This is what the equation. So if you want to write the equation for V1, it is L1 times of di by dt. So that's what you are going to write here. Your V1 expression becomes L1 plus di by dt. Similarly, your V2 expression becomes L2 times of di by dt. Now what can we write for the source? Let us assume the source will have the L equivalent value. So you will write that as a L equivalent times of di by dt. Now in both the terms di by dt is existent. In both the terms di by dt is there. So if you take the common of that di by dt, you will get di by dt of L1 plus L2. Now this di by dt will get cancelled. So finally you will be getting the equation L equivalent equal to L1 plus L2. Now this equation is same as resistors equation. Okay. However, the resistors are connected in series. We have used the formula R equivalent equal to R1 plus R2. In a similar way, if the inductors are connected in series, you will do the same way. That is, you will just add the inductance values L1 plus L2. Now the general case. If n number of inductors are connected in series, now we will get the formula L equivalent equal to L1 plus L2 plus and so on Ln. In the same way, you just have to apply the KVL for the network and write the voltage equations in terms of the inductance, and di by dt terms get cancelled. Finally, we will get this expression. Now, let us move on to the parallel combination. Now we need to write the current expressions. Since we have more currents in the network, we will go for the KCL. That is one tip. Okay, if we have the more voltage values, especially the series circuit. For series circuit, we will preferably use the KVL. For the parallel circuit, mostly parallel circuit will have the majority of the current sources and branch currents. So there we go for the KCL. So if you apply KCL at this node point, so you will have some of the entering currents is Is equal to leaving currents I1 plus I2. Now we need to write the current expression. Again we require the base equation. What will be the current equation for the inductive element? So that also we have seen, it is 1 by L integral v dt. Okay. So the formula is 1 by L integral V dt. That means I1 will be equal to 1 by L1 integral V dt because voltage remains the same for all the branches. And your I2 expression becomes 1 by L2 integral V dt. So now let us write the equations. Your I1 becomes 1 by L1 integral 0 to t V dt, and your I2 becomes 1 by L2 integral 0 to t V dt. Now this term is same, so you can take common, and the right side expression, this will be L equivalent. Then we can find 1 by L equivalent integral V dt. Now take the common of this factor, and if you strike out both these terms, now the remaining term will be 1 by L equivalent equal to 1 by L1 plus 1 by L2. Okay. So this can be simplified to L equivalent equal to 1 divided by 1 by L1 plus 1 by L2. The same thing can be written as L1 L2 by L1 plus L2. Similarly, try to remember this equation instead of this. Now coming to the parallel combination of n resistors, you can represent this as 1 L equivalent equal to 1 divided by 1 by L1 plus 1 by L2 plus and so on 1 by Ln. Okay, it is same. Okay, we have written only two expressions in the previous case. Now in this case you will write for n inductance values. So now this is our final expression for inductance. Now in a similar way we will see capacitors. If the capacitors are connected in series combination, now it is a single loop and we have voltage source. It is a series circuit, so you preferably apply the KVL to this. So by applying KVL, V1, because the current is going in this way, you assumed it as a positive and negative. So plus V1 plus V2 minus Vs equal to 0. Now we need to know what is the expression for the voltage in case of capacitors. So we know voltage V is equal to 1 by C integral I dt. So V1 will be equal to 1 by C1 integral I dt and V2 will be equal to 1 by C2 integral I dt. So if you write this expression as Vs equal to V1 plus V2, and if you write this V1 V2 in terms of capacitors, you will have 1 by C1 integral I dt and 1 by C2 integral I dt. So Vs can be written as 1 by C equivalent integral 0 to t I dt. So now let us simplify. Take this factor common. Then you will have 1 by C1 plus 1 by C2. And that is equivalent to this term. And these two terms get cancelled. So finally you will have 1 by C equivalent equal to 1 by C1 plus 1 by C2. So this will be written as C equivalent equal to 1 divided by 1 by C1 plus 1 by C2. So this is just opposite to R and L. Okay, whatever we got for the parallel combination for R and L, we got that expression for the series combination for capacitors. Now for N connected in series, you will have this formula. In the similar way, you can try for the derivation. Now for the parallel combination, apply the KCL at this node. So entering current equal to sum of the leaving currents. Now current equation I1 will be equal to C times of dV by dt, that is C1 time, and current I2 will be equal to C2 times of dV by dt, and current IS, source current, will be equal to C equivalent times of dV by dt, because voltage is same across the parallel branches. Now if you substitute these terms in this expression, we will have C1 plus dV by dt plus C2 into dV by dt equal to C equivalent times of dV by dt. Now take the dV by dt as a common on RHS side. You will get C1 plus C2 and cancel both the sides dV by dt term. The final expression will be C equivalent equal to C1 plus C2. In a similar way for n branches, you will have C1 plus C2 and so on Cn. Okay. These equations are very important. Sometimes you will be getting combination of RLC networks. In that case, sometimes two resistors might be connected in series or two capacitors might be connected in series or parallel combination, or in between two inductors might be connected in parallel or series combination. So in that case, we need to find out these equivalent values. I hope it is clear. Thank you.